When we left off last Wednesday, we had started to talk about the topic of differentials. And I tried to kind of introduce it to you a little bit. So I walked you through like an equation of a tangent line, quick recap, right? Okay. So anyway, y minus fc equals f prime times x minus c, blah, blah, blah. So they're just calling the change in y delta y, the change in x delta x. And they're saying, hey, when delta x is super, super small, we can call this dx, the differential of x. And then same thing with dy. So then we end up with dy equals f prime times dx, or, in other words, like dy dx equals f prime. So it seems kind of silly, but when you see it in context, there's actually meaning to this. So anyway, this is where we left off, was on this picture where I think I lost you. So I'm going to try to re-explain this again and see if I can get you back. The first thing, I don't know if I should explain it with the picture first or with context, but context, okay. So delta x, if you remember, I gave you guys a warm-up last Wednesday. It was a middle of the class warm-up, but it was with quilting squares. And we said, hey, what if the length of a side of a square could be off by 0.1 or 0.01 inches or something like that? What is the highest possible area that we could get, error we could get in the area of our square, right? So this delta x, that's like the error in your input. That's like the, you came. You both are here. I was told that you guys were on vacation and were not going to come back today.
We just got back.
So, and you came to math class. Way to go. Well, welcome. Okay. So you have an x value, an input value that you want, but there is a possibility for error. So delta x is like your possible error with your input. For example, in our quilting squares, it would be the error in the length of the side of the square, right? Delta y is the error in the output based on the error in the input. So delta y would be like the error in the area of the square, right? If that was your y function was representing area, right? So you have some delta x, which is your change in x. And in the context of the problems we're doing, this is going to represent an error amount in your input. And then your delta y is going to represent an error amount in your output. So what we found, or what I haven't found, but what other people have found, is that it is easier, especially when the problems get complicated. Like I will tell you, most manufacturing issues are not with squares. So when the problems get complicated, it's easier to approximate the error in the output using a differential than it is to actually calculate it using actual formulas and everything. So even though our delta x stays delta x, we know the possible error in the input, instead of computing the actual error in the output, we approximate it using a differential. So dy, that's the change in y on your tangent line as opposed to the actual change in y on your function. They're both pretty close. Remember, as long as delta x is pretty small, then your tangent line and your function should be pretty close to each other. We kind of talked about this a little bit last year with linear approximation, when we used tangent lines to approximate just the y values. Now, instead of using the tangent line to approximate the y value, we're using the tangent line to approximate the change in the y value. So, okay, except that's just with two variables, and pretty soon we're going to get into multiple variables. Does that help a little bit? Do you guys kind of get the picture? I can't tell. Yes or no? Kind of. You have a function, right? Change in x, change in y, but instead of computing the change in y mathematically using the function, we're going to use the tangent line to approximate the change in y instead. Okay. Yes.
Wait, so no tangent-wise, which one is like the approximation, which one is the exact?
Okay, I know. In your thinking, delta should be the approximation. Delta is the exact. D is the approximation. Because dy is actually on the tangent line. Okay? All right. Okay, now, we're not going to do this because this is just like practice with one variable, so we're gonna kind of go past this a little bit. So all of these problems are me just having you guys practice finding error in different scenarios. So I'm just going to read this. Don't do this. So we did so well with our squares. We've moved on to circles. The radius of a circle is 6 inches. And with an estimated error of no greater than 0.02 inches, what is the worst possible scenario for error in the area of our circles, right? Error in the area. All right. So the way you would do that normally is you would find the regular area, the ideal area that you want, right? Which would be 36 pi square inches, right? Okay. Then you would calculate the area with the maximum error for your input put in. So you would do pi times 6.02 squared, right? And then the difference between that would be your error. Okay. All right. However, and that's just me like doing more examples, right? Volumes and all kinds of stuff. However, instead of doing that, I don't know if I have, yeah. Instead of doing that, we're going to use our differentials. So, okay. So let's actually do this. The old book used to use the words propagated error, and I see propagated error a lot on the internet. The new book doesn't use the word propagated. It just, I think, uses estimated. So either way, it means it's talking about the same thing. So anyway, so yeah, the whole book. So propagated error and estimated propagated error. I think propagated means built, like it propagated from the input to the output. So I think propagated means the output error, and then estimated propagated. I will tell you, your new book never uses the word propagated. So I won't use the word propagated on your quizzes or your tests. Ooh, I might have on the quiz. I rewrote a bunch of quizzes this weekend for this unit. And I can't remember if I took propagated off. I think I left it in. Okay. Well, anyway, that's okay. All right. So we're just going to do one together, kind of using just single variables, and then we'll start bridging into where we're going to today. So, a company produces cylinders whose heights are twice their radii. If the radius of the produced cylinder is 10 inches with an error of 0.25 inches, what is the propagated error of the volume? So that's the error in the volume based on the error in the radius. All right, so if we have a cylinder, all right, and the radius is supposed to be 10, and then the height is supposed to be twice the radius, the height is supposed to be 20, right? So the first thing you would do is you would find the volume, let's see, based on those numbers, right? So you find the volume based on a radius of 10 and a height of 20. What's the volume of a cylinder? Pi r squared h. All right, so everyone take a second, find the volume of the cylinder with the nice numbers. All right, everyone good with finding volume of a cylinder? So now, to find the propagated error using traditional methods, we would put in our maximum possible difference, always go up. You can go do the plus or minus, but the plus is always going to give you the bigger error, and since we're finding the maximum possible error, you go big. So if the radius has a possible error of 0.25 inches, we would use a radius of 10.25, and then what would our height end up being? 20.5. I should put this, like, get this as a decimal so you can see the actual.
No.
I get 6.8921 over 32 pi inches cubed. I'm going to convert these to decimals though. Times. All right, so for this I get 6766.3-ish. And for the other one, I get 6283.19-ish. Okay, so my propagated error, always such a hard time saying that word. 6766.3 minus 6283.19. So around. So I get around 483.118 cubic inches. Yes. That is that's the maximum possible error based on this input. That's the exact. Now we're going to do the same thing with differentials. Okay, so part A was just kind of practicing with exact. Now, okay, what is the estimated propagated error of the volume? So now we're going to do the same thing, but we're going to do it with differentials. So for part B, so we have volume equals pi r squared h. We have to get this down to one input variable for this problem. Later on today, we're going to learn how to do total differentials, and then we won't have to. But right now, we're going to get it down to one variable. So that's why they told you that the height was twice the radius. So you could just rewrite this as pi r squared times 2r. So you end up with 2 pi r cubed. So then your dv, if you want me to put dv dr and then move the dr over, can I just put dv? I'll put dv dr. All right, dv dr equals 6 pi r squared. So our dv is 6 pi r squared dr, right? All right, so 6 pi times our radius, which was 10 squared, times the change in the radius, which was 0.25. So you get 6 pi 100 so you get around 471.24. So the actual error in the volume was 483.118. The estimated error using differentials was 471.24. Which way do you think is easier? The differentials is way easier. It's way easier. So that's y, even though it's not exact, it's an approximation, but it's an easier way to approximate error than using the exact method with all the geometry, especially when we get into the harder shapes and the multiple variables. All right, so that's the lead-in to what we are doing today. Oh, we don't need to do big fuzzy dice. Okay. Okay. All right. Okay. So now we're going to get into putting it together, which, oh, and I have a video too. Okay. So for really small values of delta x and delta y, you can use the approximation delta z is approximately dz. So we're doing the same thing as that we just did, but with multiple variables. By the way, I did not have the font for the del symbol when I was typing this, so this is supposed to be partial. It's just, I didn't have the font here. I can write over it. Del. There we go. Okay. All right, so partial z, partial x, that's the slope of the surface z in the x direction. We already know this. Partial z, partial y, that's the slope of the surface z in the y direction. So dz represents, this is where I have to show you the picture, the change in the height of a plane that is tangent to the surface at the point x, y, z, essentially. So the change in the height of the plane tangent to the surface, it's your change in your z value based on the changes in x's and y's. All right, so I'm going to try to show you this with a picture. Okay, so now it's the same as that cute little tangent line picture, but now we have two inputs. Okay, so, and I actually drew up, this part, like this little shape here, I copied from an image in the book, and then the rest I drew in with lines and little dots and stuff. So, okay, so here's what we have. We have a point, x, y, and we have a point on the function that corresponds to this point. So xy is some point in the xy plane. This is the z value, right, that corresponds to that ordered pair. Then we have a change in x and a change in y. So we have some sort of an error with this input and some sort of an error with this input. So because we've got delta x's and delta y's going in, we end up with, this is the new point for the x, this is the new point, and then, let's see, here. This is the new point, the actual new point on the function. So like these, that would be the real one. So that's your actual total delta z based on the new input with the error in the x and the error in the y. So this is your new z output value on the actual function. The estimated z value or change in z value would be if you did a plane tangent to the curve at that point. So instead of a line, now we have a plane, right? So you do a plane tangent to the curve at that point, and then you use your, how do I say this, your new input on the tangent plane to get your dz value, which is your approximation for your delta z. Rishi sees it. He's giving me the head nod. That's good. Okay. It's just like the tangent line in 2 dimensions, except instead of using a tangent line, we're using a tangent plane. Okay, Ron's giving me the head nod too. I've got 2 head nods. No? You won't give me the nod? All right. In all honesty, if you don't get it, it's okay. You can still do the problem just fine. Right? Okay. So, all right. So do you remember I taught you last Wednesday we learned something called a total differential? That's what we're calculating here. We're calculating the total differential on z based on the partial derivatives for x and y times your delta x and your delta y. Delta x and your delta y, those are the actual changes in x and changes in y, meaning like the error in your input variables. Right? And then these are your partial derivatives. Okay. And whenever you're plugging in numbers, like these numbers are always ideal. These are the numbers you want. These are the error amounts. Just like in that last example, the number I plugged in was not the 10.25, it was the 10. Right? You plug in the good numbers, but then you multiply by your error at the end. Okay. All right. So where's the okay. Oh, video. Oh, yeah, press play the video. Let's see. Let me hook up sound. All right. I played this for myself last week, but I forgot which one it is. It's been a week. Oh, let me turn this on. So I don't remember which video this is. Oh, I remember this. Okay. So this isn't, it doesn't have pictures. It's a guy explaining differentials mathematically, but it's kind of good. So he's teaching total differentials, and it's kind of a good explanation. He does a much better job than I do.
So for instance, if f is made up of x and y, then the change in x, the change in f rather, is going to be a function of the change in x and the change in y. What also matters is the slope, how rapidly f varies with x, and how rapidly f varies with y. So in both cases, we're multiplying the slope by a change to get how much the change in f due to y is, and the slope and the change in x to get how much of the change in f is due to x. And we put them together, we get the total change in f. This is kind of like if you imagine maybe looking at a map. And we can walk in two different directions, and the map is a map of a mountain. And the mountain is really more of a ridge, right? It's not a symmetric mountain. And if you were to walk north from the peak, you can see there's a very, very steep slope. And so for a given distance, you're going to go quite far down. On the other hand, if we go east, we see that there's a very gentle slope. Now, in reality, you might find it's more likely that what we do is sort of a combination. We'd move both north and east. In that case, there'd be, if we wanted to know how far down we went, we would use an equation just like this one up here. We multiply the slope in the north direction by how far north we walked, slope in the east direction by how far east we walked. Okay, and this is a general principle. If we have a function that has 3, 4, 5, 6, or even more variables, we can just keep adding terms to the total differential. Let's go to the next page. Let's apply this to a concrete situation. Let's look at the total differential of internal energy. So we can write the internal energy as being composed of two variables, temperature and volume. And so take a minute to think about how you'd write the total differential. I think I'm going to stop there. I think it was just the cute little walking example that made it nice for me. Did that help at all? No? Yes? Not a bit? A little bit? A little bit? Not really? Some? To some degree? Okay. All right. All right, well, anyway, let's go ahead and do we're going to start with a simple one without context. We're just going to do this nicely with numbers, and then we'll get into geometry. Okay,
So use the differential dz to approximate the change in z. If z is the square root of 4 minus x squared minus y squared, hey, what shape is this?
Hemisphere.
It's a hemisphere, right?
Hey, that's your boy.
Okay. All right. As xy moves from the point 1, 1 to the point 1.01, 0.97. Compare this approximation with the exact change in z, which would be delta z. So go ahead and take a minute or two and see if you can find, just write up your total differential. So you're going to find, remember, your partial x times dx plus your partial y times dy. Yes.
Is it today, like when we're going to learn why, like the tangent line, the direction of the tangent line is like the common level of the thing that we did last class?
Are you talking about the gradient?
Not the gradient, like so you know how like for the equation of the plane you said that like the direction vector for the tangent line would serve to like the orthogonal vector, like
Yeah, that has to do with the gradient. Yeah,
that's not today.
that is not today, but it is this week. So today we're going to do differentials. Tomorrow we are doing, tomorrow's quiz day. So I rewrote all the quizzes for chapter 14 over the weekend. So tomorrow will be quiz day. Wednesday is chain rule. And then Thursday and Friday is when we do directional derivatives and gradients. Oh gosh, no. We have so much more.
Oh,
Yeah. Monday is, a week from today is when we do absolute extrema on a closed bounded region. So it's just like absolute extrema on a closed interval for regular, like from last year, except now it's with multiple variables. All right. So, oh, that's me actually doing the exact change first, the actual delta z. So, so just so you know, when it says compare with the actual change, the actual delta z, that's you doing it the correct actual way, where you plug in, you plug in your old numbers for z, you plug in your new numbers for z, you subtract, and you get the actual change, right? So that's me doing that first. All right. So to get the approximated change, so the first thing I was pointing out to people is your delta x or your dx would be 0.01. It's the change in your x. Your delta y is negative 0.03. It's the change in y. And notice since y is going down, it's going to be negative. Okay. All right. Let's do partials. All right. So partial x. Had to do a little chain rule stuff. So I got negative x over root 4 minus x squared minus y squared. Is that what you guys got? Good. Partial y should be exactly the same, right? All right. So you got your partial x, you have your partial y. So your dz, I put in the numbers first. I didn't write it all out. Hang on. I want to see if I wrote it out. I didn't. Okay, I'm going to write it out up here. So my dz equals partial z partial x dx plus partial z partial y dy. So that's my total differential for z. So partial z partial x, when you're plugging in here, the number you plug in here is the ideal number. That's the 1, 1. Same thing here, 1, 1. And then your dx, or your delta x, would be 0.01, and then your dy, which is your same as your delta y, is negative 0.03. So does that make sense, what you're plugging in? So this is this isn't dz dx, this is partial z partial x. This is the partial derivative. Does that make sense?
Yeah.
Okay.
So
Times,
del z over dx.
it's del z del x times dx.
So it's the derivative of the partial dx, right?
It's the partial, this is just the partial derivative with respect to x.
Oh yeah.
How do you write the partial derivative of z with respect to x? Del z del x.
Some weird fraction.
So then we have so the total equation is just the partial derivative of x plus the partial derivative of y, right?
It's the partial derivative of x times dx plus the partial derivative of y times dy. And dx is the same. If you want to write delta x, it's just that, you know, and I have them both. I have delta x on here. You can write delta x or dx. They're actually the same. So I will just tell you that in the future, we would never write deltas. We would just write dx. Does that help a little?
I'm just confused as to like why we are multiplying by delta x or dx.
So,
Like the y behind
that's why I was hoping the video would help a little bit. So, if we do partial z partial x times your difference in x, what you're getting is the slope of your z in the x direction times how far you went in the x direction. When you do the slope of z in the x direction times how far you went, you should get the change in z in the x direction. Then when you do the slope of z in the y direction times how far you went in the y direction, you should get the change in z in the y direction. So when you add them together, you end up with the total change in your z value. Does that really? Okay. All right. Okay. Anyone else need me to say that exact same thing again?
I'm good.
Yes?
I'm good.
Yes? Okay. All right. So let me kill this. You know what? I'm going to show it on the other picture. Let's see if this helps. Because I don't think I can draw it myself. So here's what we want. We're trying to approximate our change in our z value based on some change in x and some change in y, right? So we have a function with multiple inputs. So in the case of our cylinder, it could be like radius and height, right? And then our output is volume. Okay, so we have some error in our radius, we have some error in our height. We want to know what the error is in the volume based on those two errors. All right, so the actual error, if we were to do it by hand, you would just plug in the original, like x and y, the ideal one that you want, and then the point with the errors, right? Find the volume with this guy, find the volume with this guy, subtract, and you get the error in your volume, right? But what we're talking about today is approximating it. So instead of finding the actual error, what we're doing is let's see, to get from here to here, so that's our change in x. So if I do the slope of this line times how far I travel along the line, what I get is my new y value. It's like it's how, okay. Let's see. If we ignore the fact that it's a plane and just think of it as a line, right? So think of it as like my y equals my slope times my x, right? Pretending that that's the origin. Okay. So if y equals the slope times the x, then if I multiply the slope of this line times how far my x has changed, it's really like change in x. I should do like change in x, right? So then what I end up with is my new y value. So I end up, in this case, instead of y, I'm using, it would be z. So if you think of it in just two dimensions with an input and an output, so If I do slope times how far I've gone, I get my new output value. Same thing now in the other direction. So if I do, if I do slope times how far I've gone, I get my new z value. If I take this change and add them together, that's the total change in my z value from where I started to taking both errors into account. Where
Errors of x and errors of y.
Yes.
The first section is the error in x.
Yes. Yes. And the second would be the error in y. Now, there's no way I could show this visually if we add more inputs, but you can have change in multiple inputs. It's just that I can't show it because it would be more than 3 dimensions. But you can. So if you have something, it wouldn't be a physical object, but if we had, well, I guess you could do, we're about to do volume of a box, length, width, and height, right? 3 inputs, right? So then you would have partial z, partial L, right, times the change in your L, plus partial z, partial W, times the change in your W, plus partial z, partial H, times the change in E. And then when you add all those together, the total change in z based on L, plus the total change in z based on width, plus the total change in z based on height, add them all together, that's your total error for z. Okay. All right. So anyway, so back to this problem. So my, what I did here is I found my partial z partial x by plugging in the 0.11, and that's, which was -1/√2, and then multiplied it by my delta, my actual dx, which was 0.01. And then I did the same thing here, partial z partial y, which is -1/√2, times my delta y, which is -0.03, add them together, and my estimated change in my z was 0.01414. Yes.
So the initial point is always going to be the ideal point, because you know how
Yep. You always start with your like the numbers that you're going to plug in would always be your starting point, and then the way that you take this into account is with your deltas, these guys. Okay. Good. Okay.
Can you scroll down just really 1 second?
Yes, absolutely.
Wait, no, scroll down.
Oh, scroll down. I thought you said slow down. Okay.
All right, we good.
Are we? Just checking answers? How did you do? Yeah? Okay. All right. You ready to try one with just some, it's light geometry. But your quiz will not be as light. So, okay. You want to try these on the whiteboards?
Yeah.
Absolutely. I think that'd be great. Okay. Possible error in measuring a rectangular box is plus or minus 0.1 millimeters. The dimensions of the box are 50 by 20 by 15. Use dV to estimate the propagated error. We'll talk about relative percent error in a minute. Right now, just do the propagated error, the estimated propagated error for your box. And guys, just do the plus 0.1. You don't have to do the minus 0.1. All right. Okay, let's take a look at what we've got. So the first thing that you need to do is write a formula for volume of a box, which everyone put X, Y, Z. We have some LWHs. Okay, that's fine. All right. See, this is where, oh, I'm frozen. All right. Okay, so then I like this group. They found their 3 partials. So this is me just finding the actual volume because we're going to need it for projected error or for your estimated error, but that's okay, or your percent error. All right. So so here's my partial. So partial x, which is yz times delta x, plus partial y, which is xz times delta y, plus partial z, which is xy times delta z. And then you're just plugging in all the numbers, right? So your change in x, your change in X, your change in Y, and your change in Z are all what? 0.1. 0.1. So I see some 0.01s. Be careful with that. Oh, did I convert this? Oh, that's so evil. Oh, I wonder if I got it right in here. Oh, I did. Yay. Okay, that's well, I pay attention to units. All right. So, so 0.1 millimeters is 0.01 centimeters. And they're all the same errors. So you're doing, there we go. So xy times or yz times 0.01 plus xz times 0.01 plus xy times 0.01. All right. So your estimated propagated error would be 20.5. You guys did it in millimeters. Okay, so 20,500 cubic millimeters, 20.5. Make sure it's centimeters cubed. Okay, 20.5. You can put units. That's okay. Good. All right. So let's do. All right. So we haven't talked about the relative error. So the relative error is the propagated error divided by the desired amount. So, which I think, a lot of you guys got without me even teaching it to you. So, well done. You guys didn't do it. That's okay. All right. Oh, you did percent error. Okay. So well done. Okay. So the relative error, it's your change in your Z value, or in this case your volume value, divided by the desired volume amount, which would be your volume with just the original numbers plugged in, with no change at all. All right. So I was thinking we needed to do at least one more good problem. So while you guys were working, I was kind of looking through WebAssign to see if I could find one more fun problem, because I think we need to do one more. And then I accidentally I accidentally hit the record button and backed up the recording and then shut down Chrome and had all these issues. So let me see if I can find what I was doing. Okay, so while I was looking through the problems, I found a cute one on resistance and another one that looked kind of fun. Okay, let's just create. Yeah, like ohms. Ohms. Okay. Next. Okay. But I don't want to give you a problem that I actually assigned. Cylinder. Okay. Pressure. This one's actually kind of easy because it's the same thing you've been doing. It's just changes in amounts. I haven't tried this one. So this one with the resistance. So I thought this one might be fun to try just to make sure we can all do it, because I haven't done these ones where they give you a percent. I don't know if I assigned this one for homework or not. So let's just do it now and we'll see what happens. So I'm going to make this. Okay. Talk about resistance. All right. So if R is the total resistance of 3 resistors connected in parallel with resistances R1, R2, R3, then 1 over R equals 1 over R sub 1 plus 1 over R sub 2 plus 1 over R sub 3. If the resistances are measured in ohms, R sub 1 is 20, R sub 2 is 10, R sub 3 is 100, with a possible error of 0.5% in each case. Estimate the maximum error in the calculated value of R. Round your answer to 3 decimal places. So, see what you can do with this. Do you want to do it on paper, or you guys are dying to do it on boards? That's so funny. My other classes never want to get up and do things on whiteboards.
I'm active, you know?
Okay.
Just wanna save cheese.
Okay. You need to have something in your notes, though, right?
Yeah, we already have that one
I know there's an easier way to do this. I think the easier way requires chain rule that we're going to learn on Wednesday. So I'm very proud of all of you for getting it right, solving it for R when it was quite a complicated problem, and I'm very thankful that I didn't assign this one for homework. So, but good job for all of you guys who got it. Well done. Yes.
Like, when is the crazy day where we like learn the applications like for like the airplane stuff?
Crazy day where we learn the
Did you say
Huh?
like some crazy day where we like the
airplane stuff.
Good job. Good job.
Yeah, no, I think
So,
it's today.
okay, so here's what we're doing, if I remember right. So Wednesday's chain rule. That's just a regular day. That's just like straight up calculus rule stuff. Thursday and Friday is when we will. Oh, I know what you're talking about. You're talking about the heat-seeking particle.
Okay, yeah, that's
Yeah. Okay. That always makes me think heat-seeking missile. But the ones that we're doing is just a heat-seeking particle where you're like you have some source of heat and you have a particle moving towards it, right? Yeah, that's Friday. Okay. So Friday you get to do your heat-seeking particle problems. So directional derivatives and then the gradients. The gradient's the big nag daddy.
Friday, right?
Friday. And then Monday and Tuesday are extrema. Monday is absolute extrema. Tuesday is relative extrema. And then I think we have a day of optimization applications, right? I'm trying to remember everything that's happening.
I don't remember.
Oh, and then we do Lagrange multipliers for extrema, right? So you're actually going to like Lagrange when you do Lagrange multipliers. And then I think that's it for the unit. So, and then the semester or the term ends like the following week. So we have our last test and then the term ends, right? So we'll have review and then end of term.